Sure do. Well, let me begin by thanking the organizers for this chance to speak here, particularly Fabian, Giuseppe, Denis is somewhere, I don't know where Denis is, and Armand. So I'm going to be talking today about some numerical work on two-dimensional strongly correlated systems, trying to understand their non-equilibrium behavior. And this work, as you will see, will involve a combination of using matrix product state techniques combined with information or data coming from integral field theories and or conformal field theories. Now this work has been done with several people. The person who deserves the most credit is Andrew James, who's a postdoc at the London Centre for Nanotechnology right now, and you can see this is a recent picture of him with his new daughter, who was born 3 weeks ago. He's the one responsible for writing most of all of the ITBD and IDMRG code that the simulations that I'll be telling you about today were run with. Andrew Hallam is a graduate student at UCL who's been working with us on these quenches in coupled arrays of Luttinger liquids. Of course, J.S. Coe, my longtime collaborator in the back row. He's not been so much involved with the field theory, but he is involved and will be involved in the future, and particularly when we move from studying coupled field theories to studying coupled integral lattice systems like coupled Heisenberg chains in order to get to 2D Heisenberg. So this work has, I guess, two themes or two motivations. One is to develop a new approach to studying non-equilibrium behavior in 2D systems. Now, of course, we know that studying just equilibrium behavior or in any two-dimensional strongly correlated system is hard. It's, of course, much more difficult to study non-equilibrium behavior in 2D systems. And so the way we will sort of chip away at this problem in the work that I present in this talk will be to combine matrix product state technologies together with, as I said, information coming from integrability to sort of combine the two and see what progress we can make. Now, so part of the talk is methodological. The other part of the talk will be applying this methodology to studying the Loschmidt echo in various 2D systems. Now, we've heard this quantity mentioned a couple times over the last few days, but here I'll give it for completeness. The Loschmidt echo arises in the context of quantum quenches, where you imagine having some state of some initial Hamiltonian, typically the ground state, but it can be any eigenstate, and then you suddenly switch the Hamiltonian at time t equals 0 and evolve this state, which is no longer an eigenstate of the system, with some new Hamiltonian. And then you ask the question, when does the state under this time evolution return to itself? And this quantity is called the return probability. And why this quantity is interesting for our purposes is that it's been argued that if you quench through a phase transition, that this return probability can exhibit zeros, and that this is a signature of what Heil, Pokovnikov, and Karine called a dynamical phase transition. And so what I will do in this talk is I will explore this phenomena in arrays of coupled quantum Ising chains and in coupled Luttinger liquids. So here's an outline of the talk. I'm going to begin by being pedagogical and telling you a little bit about matrix product states in 1D and 2D. And the purpose of this is really just to sort of orient you as to what I'm going to be doing with matrix product states in the context of 2 dimensions, and what the problems are and how we intend to solve the problems of using matrix product states in 2D. So that's more just to sort of set the scene. So then after having set the scene, we'll move to using matrix product states to study 2D systems, and we've come up with a useful, easy to remember acronym, CHAMPS, Chain Array Matrix Product States. And then we'll apply, as I say in the last half of the talk, we'll apply this to arrays of quantum Ising chains and arrays of Luttinger liquids. So let's start right at the beginning and talk about matrix product states in one dimension. So why do we need matrix product states at all? Well, if we have a general many-body state in one dimension, and we try to write down the corresponding wave function, we see that we need, in general, a huge number of numbers to describe this wave function. In fact, if we're trying to describe a wave function of a lattice model with n sites, then in general we need, and each site has a physical dimension small d, then we need d to the n numbers to describe this state. Now, at least, I mean, this is a lot of numbers, but at least for a certain number of states, particularly states like the ground state or states that are low-lying excited states, we won't need d to the n coefficients to describe such a state. So we need representations of wave functions that can take this fact into account. And that's exactly what a matrix product state does. A matrix product state has this form. It has, as most of you know, it involves n sets of D matrices, small d matrices, where again d is the physical dimension of the site, the number of physical degrees of site of the Hilbert space that each site in the lattice model has. Each of these matrices is large d by large d. D is what is called the bond dimension. And so if you just count up the number of parameters that this matrix product representation gives you for the state, you see that you have small d times n times big D squared parameters versus our originally exponentially large number of coefficients to describe a general state. So this is a much, much smaller number. And if we can get away with using the matrix product state to describe the state of interest, then we will be in good shape, or much, much better shape. Now, generically, this will be enough if we are interested in describing states which have small amount of entanglement in them. As, again, most of you know, a 1D matrix product state with bond dimension big D can describe a state that has log D of entanglement. And in general, states that are gapped or are coming from a gapped model and are low energy will generically have bounded entanglement entropy, and so provided we choose D large enough, which is easy enough to do, we can use this matrix product state to describe the state of interest. And so in here particularly, you know, we know that the entanglement in a ground state for a gapped system is bounded by the log of its correlation length. Now, so certainly MPS states can be used for gapped systems, but in fact, I think it's fair to say that MPS states can be used fairly efficiently to describe ground states of gapless systems, because even though the entanglement entropy in a gapless system scales as log over L, in order to describe this entanglement, it just means we need to choose a matrix product state with bond dimension that scales as some power of the system size, not exponential. So this is still very, very manageable. Now, what happens so everything is good for one dimension using matrix product states. That's sort of the bottom line. But now what happens when you go to 2 dimensions? Well, in 2 dimensions, things become more problematic, because in a one-dimensional system, when you consider the entanglement entropy, you're just cutting the system at one point. And that really restricts the amount of entanglement in the system. But in 2 dimensions, by the area law, when you cut the system into 2 pieces, the entanglement is going to go as the length of that boundary. And so if you're going to have an MPS state that describes this 2D system, it means you're going to need to choose its bond dimension to be exponentially large in the length of this boundary. And so as the system becomes bigger, your life becomes more miserable. And so generically, using MPS states in 2 dimensions is hard, no matter how you formulate it. Now, sort of the aim of this talk is to convey a way of getting around this problem of using MPS states in 2 dimensions. Yes?
So the entanglement grows with the area.
Yeah.
That's because each bound kind of has an entanglement contribution. But why does that imply that your last formula, that this D should go exponentially? I mean, I would...
Well, because you know that a matrix product state can describe a matrix product state can describe an actual eigenstate of the system it can describe it accurately if that state has less than log big D entanglement entry, or big D. So in order to, if I have entanglement entropy going as the length of the boundary A, then I need to make D exponential on A.
So every column will be a matrix. That's what you're thinking about. You one-dimensionalizing the whole thing. It's not a network with the matrix.
No. There are generalizations of MPS states to 2D, PEPs, as Ignacio talked about 2 days ago, and they are PEPs is naturally able to describe the entanglement entropy in 2D, but the problem with PEPs is that the computational costs for MPS states, the computational cost scales as D to the cubed, whereas the computational cost for PEPs scales as, I don't know, D to the 8. So it's hard. So you pay a price by going to PEPs, even though the PEPs wave function is naturally able to describe 2D entanglement entropy.
It's still better than exponential, though, right? Yeah.
Well, D to the 8 is pretty. For practical purposes, for computational implementations, D to the 8 is bad. And as far as I know, no one has ever done time evolution with PEPs. They do, in principle, it should be possible, because the way they figure out the ground state with tensor networks is that they do some imaginary time evolution. They take a randomized state and then they just apply the imaginary time evolution operator to sort of project the state into the ground state. So they should be able to do real-time evolution, but I have never seen a paper where it's done.
Sorry.
Yes.
I thought that in 2D you also have the problem about contraction. When you compute scalar products, for instance. In 1D you just do matrix multiplication. There is a natural way to do it.
Yes, I think you're right, but you mean for PEPs?
I'm wondering if in this case you have it or not. This is
No, I will not. That sort of issue will not come up for me.
Okay.
Because well, as you see, I will be using effectively 1D matrix product state algorithms. Okay. So, how do we get around this area law problem? Well, we can't certainly just move it completely to the side, but the way we approach the problem is that we have 2 strategies. One strategy is to take as much analytic information as possible and put it into the problem before we do any numerics. So that's sort of one important strategy. And then we use field theory, field theoretic representations that allow us to minimize the system size that that allow us to work with relatively small systems and still be in the thermodynamic limit. What the field theories do is they make the finite size scaling behave exponentially. So, or the finite size corrections are exponentially suppressed. So using field theories is actually to our advantage, because then we can keep the system size small. Particularly, we can keep the length of this line small, so reducing entanglement entropy, so making the numerics more robust. So how do we exactly implement, or how do these two strategies come out in the wash? Well, what we basically do to study the 2D system is we envision the 2D system as a set of one-dimensional chains. Here, the chains are assumed to have periodic boundary conditions, so they're drawn as rings. Each of these chains is some relativistic, in our case, some relativistic field theory. So either a 1 plus, either for the two examples we have, either there'll be the continuum limit of the quantumizing model, so a Majorana fermion, or there'll be a Luttinger liquid, so just a free boson. Although in principle they could be any field theory. There's no restriction. And so then we basically then couple the chains together using a 1D DMRG algorithm. The J-perp is the coupling. One of the advantages of working with analytic representations of each of the chains is that we can compute the matrix elements coupling the chains together exactly, or we have analytic expressions for the matrix elements coupling together to the chains. So that's another way we import sort of analytic information into the problem. Now, one could imagine doing this with a lattice model. One could imagine taking sort of chopping up a 2D lattice model into 1D lattice chains and coupling them together. Now, the problem there one would encounter would be that the dimension of the Hilbert space of each of the one-dimensional chains blows up. Now, of course, that's also true for us. The Hilbert space of each of our continuum chains is infinite, and so we have to deal with that fact. But we have a definite way, or a definite approach to deal with this fact. First of all, we know analytically the spectrum of each of the chains. We can write down all the states ahead of time. So we can order these states in energy, and then we can truncate them. And tossing away the high energy states. And the reason why this works, or this will work when the coupling between the chains is some relevant operator. And for the two examples that I'll present to you, that coupling is a relevant operator. And sort of the reason why this is a good approximation goes back to this very, very, relatively old work by Yurov and Zamolodchikov, where they effectively invented the truncated conformal spectrum approach, where in this paper they were studying perturbations of a critical Ising, a critical quantum Ising model in a longitudinal magnetic field. And they found that even if they truncated the spectrum very, very radically, they were still able to get very, very accurate results for the spectrum of the Ising chain in a magnetic field.
Robert, just to be
Yep.
sure I understand, so you represent this as a matrix product state, so the matrix has an auxiliary index.
Yes.
That index is the Hilbert space of one chain, or do you understand that right? Or
No. So each matrix has a physical dimension. So and so that's that physical dimension is the size of the Hilbert space, runs over indexes the truncated Hilbert space, and then each of the matrices has bond dimensions, which are sort of fictitious degrees of freedom, and which is just exactly like a 1D DMRG algorithm. The only difference, I mean, you could imagine that the way this problem is being treated is that you're treating it like a 1D DMRG, where you're looking at a spin lattice model where the spins have many, many degrees of freedom.
Yeah.
So the intuition we get from this old work by Yurov and Zamolodchikov is that we can truncate the Hilbert space of each of the individual chains and expect to get reasonably accurate answers coming out of this procedure. Now, typically when we do the truncations, we truncate the Hilbert space to say a couple hundred states. Now, compared that to most 1D DMRG analyses of 1D systems, that's a lot of states because, people are studying with 1D DMRG, like Heisenberg chains, where the number of states per site is 2, not 100, or Hubbard models where the number of states per site is 4, or maybe Hubbard ladders where, maybe you have 16 states per site. So 100 is a lot. But when we run the simulations, what we find is there's a compensation, even though the physical dimension of the individual sites is much larger than a typical 1D DMRG algorithm. The needed bond dimensions, that the size of the MPS matrices that you need to get accurate answers turns out to be much smaller than is typical than a 1D DMRG algorithm. For quantumizing, when we're in one of the ordered phase, the bond dimensions that you need for the system is on the order of tens.
That depends on J-per.
Yes, of course it depends on J-per, but you want so when I make that statement, I want J-per, you're genuinely in the ordered phase, you're in the ordered, J-per is strong enough that you're really 2D, not 1D. But let me just, maybe the way to answer that question is that we can study the 2+1 critical transition for quantumizing chains, and even close to the critical point of the coupled Ising chain. So when you're near the 2+1 critical point, you only need bond dimensions on the order of 100. So there's, for reasons we don't entirely understand, there seems to be some compensation. The physical dimension of the problem is much larger than is typical, but the bond dimensions that we need tend to be much smaller.
The area law is satisfied, or?
Sorry?
The area law. You satisfied?
Yes, you can see the area law is satisfied. So you can imagine, cutting the system here and having for different lengths chains, you can plot the entanglement entropy as a function of the length of the chains R, and you see a very, very nice linear relationship when you're in the gapped phase. Of course, there are various corrections that happen when you're close to the critical point. Now, so that's one thing we find. Now, I made reference to the fact that we're working with continuum field theories is a good thing because we can keep the length of these chains small and thus keep the entanglement entropy small, which allows the numerical algorithm to run or to work effectively. Now, the reason why we can keep the length of the chain small is because in a field theory, the finite size corrections are exponentially, at least if the theory is gapped, the corrections are exponentially suppressed. And this is, say I should have put the reference here, but it's an old result of Luttinger's where he studies field theories in finite volume. So, before I move on to discussing the non-equilibrium behavior of these various 2D systems, let me just briefly discuss an important test of using this approach in equilibrium, because you can't get it to work in equilibrium, and you shouldn't be trying things out of equilibrium. So this test will involve the 2D quantumizing model, where we imagine, well, here's our representation of the 2D quantumizing model, where we have some of Hamilton. This first term is just the individual Hamiltonians of the Ising model in each of these chains, and this is just a massive Majorana fermion. We couple the chains together with a spin-spin interaction. And of course, this 1D Majorana fermion, again, just to orient you, is the continuum version of this lattice model where you make these identifications of the lattice parameters, of the gap of the fermion and the velocity of the fermion. Now, you can run this approach and test various things on this 2+1 quantumizing model, but probably the most impressive test would be to study, or the most difficult thing you could try to do is describe the critical point. So if you imagine starting the system off where each Ising chain is disordered, and then you couple them together, at some critical value of the coupling, the system will order, and that critical point is in the universality class of the 3D classical Ising, and so that means everything is known about it. All the exponents are known to high accuracy. So you can try to measure some of these exponents, and you can measure the exponent that governs the closing of the gap, and this is known from various techniques to very, very high accuracy, probably a couple more digits than that it's known to. Particularly now that with the conformal bootstrap people, they probably know it to 8 or 9 digits. But you can ask, well, using this DMRG technique, what exponent do you get when you extract it? And you see that sort of you get not such a bad value, not a super great value, 0.65, but certainly in the ballpark. And this is sort of done with just a straight cutoff of the spectrum of the Ising chains. If you do some renormalization group improvement, you get a better answer. So you get it, but either way you take it, you get within a few percent of the actual critical exponent. So at least it seems to be working in equilibrium, would be the takeaway message from this calculation. Now, so let's move to time evolution. Now, once you've set up this scheme of using 1D DMRG to study these 2D systems, it means you can take all the advances that have occurred in the last 10 years for using matrix product states and just borrow them more or less off the shelf. And so one thing you can borrow is various time evolution approaches to studying non-equilibrium phenomena in 1D. Particularly, you can borrow the ITBD and TBD algorithms and just apply it to this problem. Apply it to studying time evolution in 2D. Now, I should add, I said earlier that no one had tried to use PEPs to study time evolution in 2D. However, there have been various attempts to study time evolution using sort of more standard MPS approaches. And I guess there's two recent works that would be useful to point out. One coming from Joel Moore's group, where when people do most of the work on lattice models in 2D that have been done using DMRG involves taking a 2D lattice model and then turning it into a 1D lattice model with long-range interactions by drawing us like a snake state through the 2D lattice. And so the issue there is how does one adapt these time-evolving block decimation algorithms to deal with Hamiltonians that have long-range entanglement. And so this paper dealt with that problem. There's sort of another approach that uses the time-dependent variational principle to study time evolution on two-dimensional lattice models. So there are other approaches out there. So what we're going to do with this time evolution is study the particular problem we're going to focus on in this talk is studying the return probability. And well, this quantity has been discussed several times already. What the return probability is you have some initial state of the system which is an eigenstate of one Hamiltonian. Then you do a quench at t equals 0. You change the Hamiltonian and you evolve the state according to this new Hamiltonian, and you ask what the probability of it after some time t of it's returning to its initial state. You can note, as people already have, John Carty, this quantity has the appearance of a boundary partition function.
How do you know it's going to return to that state? Their theorem that will, or?
No, I mean generally it won't, but sort of what people.
No, it will, but after
We get zero.
enormously long time.
Well, sure, if the system is finite, it will eventually, after there'll be some recurrence. But the problem people are interested in is when the system is infinite. So as also has been noted several times in this workshop, people, particularly this paper by Heil, Pokovnikov, and Karine, have noticed that non-analyticities appear in this quantity. So what they studied the problem of where they took the state, the initial state, some ground state of a Hamiltonian, they quenched the Hamiltonian into a different phase. And what they noticed is that the return probability had zeros, or alternatively this quantity f of t had non-analyticities. And that these, at least in the model that they were studying, which was just the 1D quantum Ising chain, what they noticed is that these zeros or non-analyticities appeared only if you crossed the phase boundary. So you quench from the ordered to the disordered phase, for example. And what they termed this was, and so when they noticed this, they termed this a dynamical phase transition. Now, Alessandro talked about other non-analyticities that can appear when you do such types of quenches, and it's not quite clear to me what the connection is between those non-analyticities and these non-analyticities, or if there is a connection. But I think, given how controversial calling these dynamical phase transitions is, it's probably useful to point out that non-analyticities do appear elsewhere. Now, you can, as has been done now several times in this workshop, you can criticize this terminology of dynamical phase transitions. I mean, one ground you can criticize is that it was only initially shown for what was basically a free fermionic system. However, sort of shortly after the initial Heil et al. Paper came out, Dirk Schurst and Christoph Karash did some work where they extended where they showed, looking at sort of interacting versions of Ising models, that these non-analyticities also appeared if and only if you crossed a phase boundary. Probably a more trenchant criticism of calling it a dynamical phase transition is that if you take this boundary partition function, the time is not really analogous to a temperature, but to a length. So It's not quite, which is, I think, if I understood correctly, why John Carty said really what you should be doing is you should be varying a parameter in the Hamiltonian in order to map it onto what we understand by as a classical phase transition rather than this time.
But you are also to send t to infinity to get a classical phase transition in this language. Otherwise, how it can be singular?
Yes.
Oh, I mean, you can't have a phase transition in a system with boundaries.
My infinite volume.
No, but you take
Yeah,
a
but
straight
direction
from
is
the
the
infinite in
other
one
direction
direction
is
with a
infinite.
finite.
Okay.
So beyond these sort of more, beyond these critiques, it didn't take people very long before they actually came up with counterexamples. So people looked at the return probability in quenches and antiferromagnetic Heisenberg chains. And the sort of quenches they looked at is where they imagine starting the antiferromagnetic Heisenberg chain in a state where delta was very, very large. So basically a Nell state. And then they quenched to a point where delta was bigger than 1, but at least finite. And what two people noticed, Jesko Serker and Maurizio, noticed is that even if you remain within the gapped antiferromagnetic phase of the Heisenberg spin chain, you can see non-analyticities. Now, so that would seem to make the association of the non-analyticities with the crossing of the phase boundary problematic. But one property that I will point out that seems to be common to both phenomena is a type of athermal behavior. Both the Ising model, quantum Ising model, and the antiferromagnetic Heisenberg model have a well-defined set of quasi-particles. The set of quasi-particles for Ising is just fermions. For the antiferromagnetic Heisenberg chain, you can just take the quasi-particles to be the various string solutions, the beta-Ansatz equations for antiferromagnetic Heisenberg. Now it's sort of an important part of the original Heil, Pokovnikov, and Karain paper was when they noticed that these non-analyticities were occurring, it wasn't just, they noticed two things. They occurred when you crossed a phase boundary, but they noticed that they occur when the fermion occupation numbers go athermal, where the occupation numbers look like you have negative temperatures. And you can actually go in for the antiferromagnetic Heisenberg quenches, and you can look at the distributions of the strings, and you can see that they are also athermal. When you see these non-analyticities, you see that these string distributions are athermal. They don't correspond to any temperature. So perhaps that's a better, at least, rule of association, that these non-analyticities occur when, particularly at least when you have some well-defined notion of quasi-particles, where these quasi-particles have athermal occupations. And so I'm stressing this because this is something we'll actually go ahead and test or explore with these arrays, this 2+1 quantum Ising model. So let's now move to this first example where we study the return probability in these coupled arrays of quantum Ising models. So the particular quench we're going to look at is we're going to have each Ising chain in its disordered phase. So that's when the mass of the Majorana fermion is negative. The initial state of our initial state will be the uncoupled chains, and then at time t equals 0, we'll suddenly turn on a coupling between the chains. And if the coupling is small, the system will remain disordered, but we can turn up the coupling large enough to pass the critical point and quench into the ordered phase. So before we do that strong quench, let me first do a simple test of this application of ITBD to the system by doing a weak quench and then comparing it against perturbation theory. And so here are the results of this comparison here. So here we're plotting the mode occupations on each of the chains as a function of time. The solid lines, well, we present data for 3 different chain lengths here. The solid lines are the results of the ITBD, and the dashed lines are the results of the perturbative calculation using this unitary perturbation theory that avoids secular terms. But so we see, in short, we see good agreement between the perturbation theory and the ITBD. So that means that at least in some sense our ITBD algorithm is working.
You understand correctly that the limit you're really interested in when you're converged in R.
Not necessarily.
But that would be your two-dimensional system, no?
Well, so yes. So large R would be two-dimensional. I mean, right now we're working in sort of a system geometry where we have an infinite cylinder because it's ITVD, and with finite circumference on the cylinder. But I guess the point I would want to stress is that we don't need to go to infinite R to see non-analyticities. Okay, so for weak quenches where we do not where we quench into the same phase, the ITVD seems to be working. Now let's quench through the critical point. So, and then ask what the return probability gives us. So this black line here is still in the disordered phase, and you see that the log of the return probability is completely smooth. However, if we now quench through the critical point, so these are the coupling, the critical coupling here. This is far beyond the critical point. The critical coupling is like 0.187, so we're deep in the ordered phase with these couplings, and we see cusps. Sort of an interesting feature, if we, instead of doing ITEVD, you just do TEVD, so you have a finite number of chains instead of an infinite number of chains. You see that the cusps occur at a different point. So the times at which the non-analyticities appear seem to be sensitive to boundaries. We also have noticed this just in the 1D case. Now, I made the point of saying that these non-analyticities seem to be associated with athermal behavior of the modes. So we can sort of back engineer this problem, and we can ask, I have my 2D system, I can compute, at least in lower perturbation theory, the mode occupation for this type of quench. And so at sort of the very lowest order in perturbation theory, this is the expression for the mode occupation. And then you can ask, well, for this, at what value of J perp does the mode occupation become athermal? And so you get this for an answer, J equals 0.27, whereas the critical value is 0.18. And so you see that you don't get, I mean, this is low order perturbation theory, but you don't get such a bad estimate of the critical value. It would be very interesting to take this perturbative calculation to higher order, which is certainly doable, and see if you move closer to the critical point. And see whether, and so in other words, whether the appearance of the athermal modes in this 2+1 dimensional system corresponds to where the actual critical point, the known equilibrium critical point that one can knows from independent calculations. So that's the return probability in two-dimensional arrays of quantum Ising chains. Let's turn to the problem, the other example I had, that namely the return probability of coupled Luttinger liquids. So each of these, so we're going to be considering Luttinger liquids as representatives of one-dimensional Bose gases. And so here's the Hamiltonian for each of these tubes. The Luttinger parameter can vary if they're to represent 1D Bose gases. It can vary between 1, where the gas is in the Tonks-Gerardo limit, so it's just basically free fermions, and infinity, where basically you have non-interacting bosons. So that's sort of the relevant range for K. We can couple the tubes. We couple the tubes through this tunneling term. And the type of quench we're going to do is very, very similar to what we did with the Ising chain. We're going to initialize the system with T perp equals 0, and then suddenly turn T perp on. Now, in these ITBD algorithms, there's no problem in doing ramps of T perp. And so we could easily tie into the experiments of the Schmied-Meyer group. Although, of course, we're doing many, many tubes, rather, whereas they have 1 or 2. So one of the things we can study are the mode occupations. And so the modes come about from looking at this expansion of the Bose field. And so the modes are these B's. And so we can ask what the time evolution of the various modes in the system are after you turn on T-perp, coupling the tubes. If you can look at the ratio of the mode occupations, and you see that they occasionally do go athermal. Actually, one thing I should note, that in the quantum Ising chain case, we needed to have a finite coupling between the chains when the chains were disordered in order to induce a transition. Here, an infinitesimal coupling will put you into the BEC phase. The only thing restricting that would be the finite length of the tubes. So for infinitesimal, for finite lengths of the tubes, infinitesimal T-perp won't put you into the BEC phase, but so there will be some finite critical T-perp, but as you make the system longer, you can move into that phase. So again, again, when we turn on the coupling between the tubes, we see cusps in the log of the return probability. So this data here is for different tube lengths. You see for the shortest tubes, at least for the times we run out to with the ITEVD, you don't see any cusps, but that could be because of just a finite size effect that you're actually, because the finite size of the tubes is cutting off the transition into the BEC phase, but for longer tubes, you definitely see these non-analyticities appear when you couple the tubes together. So, with that, I will conclude. So at least one thing I would like you to take away from this talk is that by combining integrability and MPS techniques coming from one dimension, we're able to study strongly correlated non-equilibrium behavior in 2D. This method has undergone several tests. In equilibrium, it can describe the critical point, the 2+1 quantumizing critical point, and at least for weak quenches, we can match on to unitary perturbation theory. We see that in both the coupled quantum Ising chains and the coupled Luttinger liquids, when we quench into a different phase, we see non-analyticities appear in the log of the return probability. Now, So all this work has been done with this, with coupling together continuum field theories. I think one of the more interesting directions that this work will take in the future will be, instead of coupling together continuum field theories, we'll be coupling together lattice integrable lattice models, and particularly 1D Heisenberg chains, thus sort of realizing a way of attacking problems related to 2D Heisenberg models of various configurations. Now you might say, I've sold this method on the basis of various features of using continuum field theories, but in particular the fact that we can keep the system size small and so that the finite size corrections are exponentially suppressed, and the fact that we can truncate the Hilbert space and energy and get good answers because the coupling between the 1D systems is relevant. Some of that seems to go out the window when you consider coupling between 1D Heisenberg chains. You have a lattice model, so you lose this nice exponential suppression of the finite size scaling, and the spin-spin coupling between two Heisenberg chains, which is what you would want to study, involves marginal perturbations, which is also bad for this. Nominally, you would think would be bad for this approach. But one good thing, and one thing that we haven't really used for the continuum field theories, is that with you need, as an ingredient to this, you have to have a good understanding of the one-dimensional Hilbert space of the chain. And for the continuum models, we just use this very minimally. We've only used this to cut off the throwaway high energy states. But for the 1D Heisenberg chains, we have a lot more information. We know for a given state, we know how many spin-ons it has, whether it has 2 spin-ons or 4 spin-ons or 6 spin-ons. And we have some intuition that the most important states are going to be the 2 spin-on states and maybe the 4 spin-on states. And states involving higher number of spin-ons just won't be important. So we can... Fabian disagrees.
Yeah, just a moment. So it depends on what you do. So if you do non-equilibriums, it is surely not true.
It depends how hard you quench.
So
we know in one dimension that the spectral function of the 1D Heisenberg chain is exhausted almost completely by the 2 and 4 spin-ons.
Low energy density compared to the ground state, no? So you have a finite number of spin-ons, absolutely, but if you work at finite energy density, this is not going to be true.
This is the number of spin-ons per chain. I can be at finite energy density, but if I look at per chain, still have a finite number. The point I'm trying to make is we have other knobs to play with from our knowledge of the spectrum of the 1D chain that we haven't really used for the continuum field theories, but we'll bring into play for the lattice integrable models. So that's all I wanted to say. Thank you very much for your attention.
Is the truncation criteria or the key change?
Sorry, is the
Truncation, how many stages of key? Or
several hundred.
what is the criteria?